So translation, we think of as just sort of sliding our paper along the desk to a different location. We could also think about taking that paper and turning it a little bit. I think we can agree heuristically that if I just rotate a piece of paper, I'm not changing the lengths of any of the sides on a polygon that I might have on that paper. I'm not changing the measures of any of the angles on that paper. So I think we can agree at a gut level that a rotation should be an isometry as well. And in linear algebra and in multivariable calculus, you can define a rotation about a fixed center of rotation. In the figure here, it's called B, and generally we might call it O, as our authors do. We can define the rotation about that center of rotation through a fixed angle. So the angle isn't drawn in on this diagram, but let me draw it in. The angle here is the counterclockwise angle. We'll label as alpha. So the rotation about the center B through the counterclockwise angle alpha, we would like to show is an isometry. We can define it using these nasty coordinate formulas that we learn in either multivariable calculus or linear algebra, right? We do some work to discover those. We can represent it by matrix multiplication, just to tie this back into linear algebra. Right? We can also think of this as cosine alpha minus sine of alpha, cosine of alpha, multiplied by the coordinate vector xy. And then we can do linear algebra with this matrix to understand the properties of this transformation. That's a bread and butter thing that we do in linear algebra. But it's kind of nasty, right? Because there's trigonometry floating around in here. If alpha is some nasty angle, then these cosines and sines are going to be nasty numbers to work with. And so the coordinate geometry approach to this, while it's really powerful for understanding the properties, is limiting for us. It has a very high bar computationally, and it also restricts us to working in 2 dimensions. Let's see if we can find a coordinate-free way to define what it means to rotate the plane about a fixed point, a fixed origin, through a fixed counterclockwise angle alpha. And the way we'll define it is just by using the angle that's made between the points P, so an arbitrary point that we're rotating, the center of rotation, which I'm calling B in this figure, and then P prime, the image of the rotation. Our rotation should be defined by the property that regardless of which point I started with, after I've rotated it, the point, its image, and the center have to make the same angle alpha, regardless of which point we started with. So another way to say that with notation is that a transformation is called a rotation if there exists a fixed point O. That O is what we think of as the center of our rotation. In linear algebra, that center is always the origin, because linear transformations can't move the origin, but in general, we could do it with other centers of rotation. That center of rotation satisfies that the measure of the angle from any point P to that center to the image of P has to always be the same. It has to always be this angle alpha. So this is our definition of rotation. And one of your groups is going to have the task of showing that the transformation so defined satisfies the requirement of being an isometry. So how do we know that just because these angles are always the same for all of our points, that that's enough to guarantee that 2 points in the pre-image are going to have the same distance away in the image after we've rotated them? So that's going to be another proof. We need to prove that rotations are isometries.